I mean, the first assignment is going to be like, what you're going to do is that we're going to write assignment on structure property relationship of copolymers. Okay. So what you have to do, you have to select 10 different copolymers. Okay. You can refer any stuff and you have to write such a way like there should be a table and the first column should be a copolymer name and their chemical structures and the third one should be observations what you have understood from the structure or the copolymers what you have chosen. So say for example here like polyurethane based on polytetramethylene oxide subsegments. Okay, that means the subsegment is based on PTMO and the hot segment is based on some diisocyanate. Okay, so by changing this molar ratio you can fine tune their mechanical properties as well as the other technical properties. Say for example if you choose some polydimethylsiloxane based soft segment, then you can have some sort of improved biocompatibility of your copolymer substrate. So is it clear? Can you do that? I mean, so you have to select 10 different copolymers. Okay, and of course you have to write down their chemical structures, and the third column should be observations like what did you understand like in terms of structure property relationships. Is it clear?
Yes, I think.
Okay, so the deadline can be of can you send it to me before 3rd of September, Friday? 2 weeks.
Yes,
Yeah.
sir.
Okay, so I'll set up everything in Moodle, so you don't have to send it to me by email. So directly you upload it through Moodle. Okay, fine. So we were discussing about the nanomaterials, nanotechnology, etc. Right. So this is one of the graph where you can see with the reduction of particle size or the increases of surface and area, how the melting temperature is getting reduced for the gold nanoparticles. Okay. And of course, this is a relationship between surface energy and their particle size, as well as the charges between two phases, like polar and non-polar, non-polar. Say, for example, like if you put water on the non-polar substrate, what will happen? The water will not get attached on the substrate because water is polar and the if your substrate is non-polar. So as a result, what will happen? The surface energy will be getting lowered. Okay, as a result, like the water droplet will not get addition on the surface of your non-polar substrate. But yeah, of course, if you have the substrate something of same polar substrate, kind of like biopolymers or some proteins. Okay, so what will happen? The interactions will be pretty much good because it means water will have more high surface energy. Okay, when the moment they interact with the polar materials. Okay? And yeah, sometimes it can be also called as interfacial free energy in terms of like when it comes to the composite section. Okay. And do you know what the contact angle? Say, for example, let's say, you can see like we have given there is one substrate like different color, like slightly of reddish color, and you have blue color. Water droplet. So if I want to measure the contact angle, like kind of how much the adhesion force is happening between these two material. Do you know something about that contact angle analysis or something? Have you studied this thing? No. Say, for example, I'm giving you some unknown material and I am asking you to check how much the charge is, the surface charge is there, like polarity or how much the non-polarity is present in your material, like quantitatively. So if you want to analyze that, so there is a procedure called contact angle analysis. Okay. So the moment when you put water droplet on the substrate, what will happen? You can measure the contact angle, between the substrate and the water actually here. Sorry. So this angle will be measured actually. So once this angle is very much low, means like less than 50 degree, that means the water is getting attached. It is addition is pretty much better between the two substrate. But if the contact angle is increasing, like say for example 110 degrees Celsius, etc., that means the water is not at all sitting on the surface. So there is a difference between the charges. One is maybe polar and another one is non-polar. So do this homework. Just write down the contact angle analysis or the contact angle measurement, and just Google it. You'll get to know all these infos. Fine. So if we see the the synthesis method for nanoparticles or the nanomaterials, there is two major techniques. One is called top-down approach, another one is bottom-up approach. Top-down means you are going to take some bulk metals or the bulk material, and with the help of some mechanical force, like either of with the help of high impact, like hammering or some sort of like shearing force, etc. Then through that mechanical force, you can reduce the particle size into the nanoparticles. Or there are alternatively the other options like a bottom-up approach. That means you are manipulating the atoms and then you are making some cluster kind of particles, and the cluster sizes are in the stage. The ranges of between 1 to 100 nanometers. So these are the two main approaches, and yeah, into that there are a lot of approaches. The techniques, like you can see here. So if you see the bottom-up approach, we have a various procedures, process like wet chemical synthesis, liquid solid reactions, and GPC gas condensation processing, and vapor deposition, and chemical and physical vapor deposition. And we do have hydrothermal, like laser ablation and electro deposition, etc. And we do have a top-down approach, which is nothing but high energy ball milling. Okay, it's a kind of milling process commonly used for ceramic processing. Okay, that means metal oxide based nanoparticles, as well as in the powder metallurgy, and it involves particle size reduction and solid state alloying or mixing or the blending. And the process is usually used for hard brittle materials, because if we take some soft material like plastics or rubbers, you cannot reduce them because they undergo high extensive elastic deformations. And yeah, the limitations of this approach is that since you are introducing some mechanical forces, so as a result, what will happen? There will be a lot of contamination would happen, as well as the homogeneity, like particle size reduction, will not be that uniformity. Okay, so there will be heterogeneous particle size variations. All right. What else limitations? Yeah, but since it is contaminated, with other, particles. Say, for example, if you want to introduce a mechanical force, probably you'll be taking some third, material, okay, or the other material, which is slightly harder, okay. Then only you can break the bulk metal or the material, and you can make it into the small size, like 1 to 100 nanometers. So that is how they make, top-down approach with, which is called high energy ball milling. So now, before getting into the nano composite, so try to have some basics about composite. What is composite, etc. Composite is considered to be a multi-phase material which exhibit a significant proportion of properties of both constituent, such that the better combination of properties can be obtained or realized. Okay, that means you have at least two material which has distinct phases. Okay, and both phases has extremely different properties. Okay, because you are going to obtain multifunctional material out of the the multiple properties in one composite material. That means you're going to take minimum two material and which has distinct phases as well as the distinct properties. Now the thing is that how you are trying to make interactions between these two material, that is very important to have those desired multifunctional properties or the characteristics. Okay, say for example, a composite material is a combination of two or more chemically distinct and insoluble phases. They both should not dissolvable with recognizable interface. Of course, they are not chemically attached. There should be some interface between two phases in such manner that the properties and the structural performance are superior to those of individual component or the phases. So, namely, what we used to have in composite is that one is usually the name is called matrix and another one is called filler. Okay, so matrix means you are going to take one substrate, and the substrate, the material will be reinforced with the help of filler, which is called dispersed phase. Okay, so the material I mean, matrix could be of any matrix, like metal matrix based composite, or the ceramics matrix based composite, or the polymer based matrix composite. Okay, and of course, polymer can also be referred as organic matrix. Okay? And yeah, in addition to that, the constituent phases must be chemically dissimilar and separated by a distant interface. And of course, the most metallic alloys and many ceramics do not fit this definition because their multiple phases are formed as a consequence of, I mean, natural phenomena. Because say, for example, if you see the metal oxide, mixed metal oxide, so like that will be a type. Bimetallic or kind of mixed metals. And all ceramics based mixed metal oxide. So sometimes they used to mix. The differences of those. Metal oxide, and they used to call them also. Composite. Okay. So yeah, this phenomena will come into that category. Okay. And yeah, composite again, they are a combination of two or more organic or inorganic component. That means, like you say, for example, if you take polymer based composite, the matrix is a polymer. That means the matrix will be filled by the polymer based matrix, material, and the filler should be either metal-based material or the ceramics-based material, like mixed metal oxide or any other, nanoparticle-based oxide materials. It should not be again the same kind of polymer can be used as a filler. That is not considered to be as a a composite structure. Now, so can we call Fe2O3 and sulfur dioxide as a composite material if I mix Fe2O3 and sulfur dioxide?
No, sir, I think.
Okay, and if I take some polymer and if I take some Fe2O3 based particles, will it be a composite material? Can we call them as a composite material?
I think also I can not say a composite material.
Was that hello?
Composite dissonance. Yes, sir.
Okay.
I think that we cannot say this is a composite material, the Fe2O3 or polymer. Be mixed together.
Okay, no, that it can be also called as a composite because one is polymer and another one is non-polymeric material. Fe2O3 is kind of oxide material, so can be called as a composite. Fine. So this is how they looks like. They're macroscopic structures. Like one is matrix. Continuous phase. Okay, and another one is like this dotted. Lines are considered as a dispersed phase. So see, also we can be called as a discontinuous phase. And these are the major classification of composite. Okay, so you have a composite structure, and based upon that dispersed phase or the discontinuous phase or the filler, it can be divided into three categories, like a particulate based composite and fiber reinforced composite and structural composites. Okay, and particulate means that could be of a larger particle and is dispersion strengthened particle based reinforced composite. And fiber, of course, we do have a continuous fiber and discontinuous fibers. Continuous fiber means like kind of you can see how the threads usually they used to fold it like they used to store it. So those kind of continuous the ropes and all like used to be called as a continuous fibers. That is also a fiber. They used to fabricate from any kind of polymers like polypropylene, nylon, etc. And discontinuous fibers means like short fiber. Okay, say for example like carbon tubes or some carbon nanofibers, etc. They have some defined width or the diameter, and they have got like kind of pretty much high length. Okay, of course, yeah, they're not continuous. And the aligned random, that means like continuous fibers are how exactly they have aligned in the matrix, like either polymer matrix or the metal matrix. Okay, if they align properly, that is called aligned discontinuous fiber based composite. And if they are aligned, or if they don't align properly, like random manner, fibers are randomly dispersed in the matrix, means that is called random fiber dispersed fiber reinforced composite. And structural means they have different layers, like the kind of sandwich structures. So the matrix could be of one layer, and another layer will be filled by these fillers, and then again the next layer will be a matrix, like kind of multiple layers. Okay? So this is how the typical composite looks like this. I mean, you have a filler. I mean, this particle is filler. Okay. So like matrix is called like continuous phases. Okay. So if you disperse the filler properly, that is called homogeneous dispersion. And if you don't disperse properly, like there will be a difference in the particle sizes as well as the geometry. That is called heterogeneous dispersion. Okay. So this, how exactly the things are like dispersed. Like a microfield and microhybrid and macrofield systemics. And of course, we do have a nanofiller dispersed matrix or the composite structures, which is called nanocomposites. And you can see here, like if you add very few percentage of filler or the volume percentage or quantity of fillers into the matrix, you can see the dispersion. Now the dispersion is pretty much good. Yeah, if the moment when you add more amount of fillers, what's happening, there will be a formation of aggregate structures as the nanoclusters. So how to reduce all this thing, like how to modify the surface of the nanoparticles and how to improve the interfacial interaction between the two phases. All these things you're gonna study maybe in the subsequent class. Yeah, this is how the typical, structural composite looks like this. Okay, the best example is wood. Actually, if you see wood, actually they have multiple layers and they are made up of different cellulose based component. And we do have a sandwich panel, like one may be of like kind of polymer based to sandwich, another one could be a fiber based structures. And of course, the nothing is new here again. Like it all, existed already in the nature. Just we are trying to pick something. We are trying to, have that idea for our, day-to-day life applications. That's it. So if we pick up any kind of, concrete or kind of brick, etc., and if you see their composition, etc., it's nothing like composite structures. And most of the properties of composite, they depend upon various things like constituent phases, individual phases, and relative amounts of filler. Okay, it's not that straight away you add more amount of fillers and then the property will keep on increasing. It's not that. It's not like that. The filler dispersion or the distribution is also important. If you don't have the proper dispersion, homogeneous dispersion, and if we have this kind of aggregate structure, what will happen? The track will start propagate very easily. Okay, so that means like how much amount of filler you are adding, that is really very important, and the geometry of the dispersed phase is also important. And shape and size and the particle size distribution and their orientation, etc. Orientation when it comes in the moment when you are taking the fiber-based fillers. Yeah, this is how we used to call orientation. Like you have a fiber, short fiber, and then you have a matrix, which is called composite structures. And you see the fiber directions. They are uniaxially oriented, and you can also see the distance between this two layer and the angle between the two particles or the fibers. So it's up to you and depending upon application, how exactly the product is going to experience the mechanical load or any other particular load. Okay. So according to that, you can design the fiber, geometry either in the form of cube or the rod or kind of like a spherical, etc. So by having different fabrication technique, you can align this fiber, short fiber into your matrix for having those desired properties. And the best thing about composite is that they are very lightweight and very high strength. Of course, you have a lot of options for designing the flexibility or the mechanical properties. Okay? Say, for example, if you want to, fabricate the composite material, and you know that the force is going to act uniaxially. That means if you align this fiber properly on the directions of the force which is going to be applied, so you pretty much know that where the force is going to apply. So if you align the fibers according to the same direction, the material, the property, mechanical property will be very much high. Okay. So now we do have some biocomposite. That means if you have some biological, bio-renewable resources-based material as a filler or the matrix, which is called as a biocomposite. Okay, biocomposite combines plant fibers with resins to create natural-based composite material, which means they are, renewable resources. Since the material is coming from the natural resources, they are renewable and sustainable material, can be biodegradable or biocompatible, etc. And yeah, now the business has come. Like, what is nanocomposite? Nanocomposite, again, it is a multi-phase solid material where one of the phases has to be in the shape of at least one-dimensional, material, and yeah, the particle size should be in the ranges of less than 100 nanometers. Okay, and the nanoparticles, or that could be of nanofiber or nanoclay, etc., like one-dimensional, two-dimensional, and three-dimensional, etc. So the difference between the nanocomposite and composite is that. So what is that difference? Very simple. What is the difference between the composite and nanocomposite?
The dispersed phase consists of nanoparticles.
Yeah, the particle size of the dispersed phase or the filler or the discontinuous phase should be, in the range of 1 to 100 nanometer, and the dimensions also at least should be in at least one dimensional. Okay. And since they're very tiny particles with very high aspect ratio, what's happening? Even the moment, like when you add 0.5% of filler, you can see, property improvement significantly. As compared to that of micro composite or the macro composite. Okay, and the beauty about the nano composite is that since you are adding very small percentage of filler, the volume percentage or the weight percentage, the transparency or the optical properties of the base material or the matrix will not be deteriorated at all. So the transparency characteristics will be retained. Okay. So you can see here the traditional composite, the stress strain curve, and as well as the nano composite as well as the polymer. Okay, they always have, significant of like strength as well as the elongation. That means you are not, going to lose anything. Okay. So yeah, having a small filler size, having a very high surface to volume ratio, what's happening, like improved mechanical property? That means increased ductility and without, decreasing the elasticity. Okay, high strength, as well as they have got very high scratch resistance as well as very good optical properties. So you can see here now how good the filler is dispersed actually. So this term transmission electron microscopy. Okay, and they have used a gelatin-based matrix, polymer matrix, biopolymer, and you can see here how good the filler is dispersed nicely. Okay, and then they have seen the optical properties by pushing the UV and visible rays. Okay, and then they could see that the transmittancy rate is pretty much same almost. Okay, and it was almost like reaching to 91%. That means the film is completely transparency. Of course, there is no difference, much significant difference between the pure gelatin as well as even 16.78% reinforced alumina filled gelatins. And we do have some size limits for this effect. Many people have been proposed, and so usually the people prefer less than 5 nanometer for catalytic activities. That could be of any catalytic activities. Okay, photocatalytic activity or chemical reaction catalytic activity, etc. And greater than 20 nanometer for making hard, less than 20 nanometer is preferable for making very hard magnetic soft materials. And having less than 50 nanometer is better for refractive index, or having that retaining those optical transparency of the materials. Okay. And likewise, I mean, we have a different magnetic properties as well when it comes to the particle size. Okay, so it depends on the materials also. It's not that always like if you reduce the particle size less than 100 nanometer and then you'll get super paramagnetic. It's not like that. Provided you should select those magnetic based material. It's not that you straight away you choose some calcium phosphate based material and then you're trying to have those paramagnetism. No, you'll not get. So you have to select either like manganese or some iron based material, and then if you could make the nanoparticle having sizes of less than 100 nanometer, then probably you'll reach these kind of properties like a super paramagnetism, etc. Okay, so we'll stop here. Yeah, we'll see you in the next class, and if you have any doubt, we can discuss.
So,
Yeah, yes, Pooja.
so in the beginning, you had told about the assignment. There you
Mm-hmm.
had shown a few copolymers. So
Yeah,
there the soft segment was mentioned. Like what exactly is a soft segment?
that's what your homework. You have to you have to refer some books. What is
Oh,
soft segment? Soft segment in polyurethane. Read it. See, this is was some research paper. So probably, I mean, this is my paper only. I've given some definitions here actually. So maybe I'll send this paper. You'll get to know.
okay.
So okay, that is what your homework. So if you take polyurethane, the chemistry, they have a hot segment and soft segment. And if you take like a polyhydroxy butyrate and co-hydroxy based this thing, they'll not have those kind of segment, but rather they have a different, I mean, a molecular chain element. Through that, they used to define like if you have this kind of proportion more, so you'll have those kind of molecular chain arrangement, and as a result, you will have those also kind of property increment, etc. Are you getting it, Pooja?
Yes, sir.
That's what you refer 10 different copolymers either from Google or some books and or some papers. Like go to Google Scholar and you'll get a lot of papers and start to read and so that you'll know actually by changing their I mean chemical structure or the molar ratio how one can fine tune their properties of the materials. Just like your, I mean, like iron carbon phase diagram, by increasing the percentage of carbon, you are getting so and so different microstructure, right? And that is taking you to different properties, right? The same cases here also. Of course, here microstructure as well as the molecular chain arrangement, and either it is forming any kind of like a hot segment and soft segment. That means changes in the microstructure, like one will be acting as a continuous phase, and another one will act as a dispersed phase, which is called a hot segment. So I'll send this paper. Maybe you'll have some rough idea.
Okay.
Can you add this one also composite? You write 10 different composite, I mean, this thing also examples, and then try to figure it out their properties and what are the key features people have done, or what did you understand, observations, etc. Can you add it, or it will be more, I mean, task for you? What do you think? You have 2 weeks, so it's not that tough, I guess. So you are going to write 10 different copolymers, and the second table could be this one composite, I mean, observation. Like you have to select 10 different composite and you have to write down their observations. What is the continuous phase and what is the dispersed phase, etc. Or you can take some more time also. Instead of 3, you can take 10 also if you want. Why is it fine, or you don't want to do that composite part? Oh, Prakash. Okay, somebody said fine. What's up? All right, so I'll send information through Moodle. Okay, see you then. Bye.